Hello and welcome to this lecture. This is in this module we are discussing about common probability models. And so far in the last couple of lectures we have discussed about different continuous probability distributions, and we have seen their applications in different problems of civil engineering. And in this lecture we will start the discrete probability distributions. So this discrete probability distributions that we have discussed earlier in some module, we will just use those distributions and we will see their applications to handle different problems in for the different problems in civil engineering. So our today's lecture will deal with the probability models using discrete probability distributions, and we will take a couple of discrete probability distribution. For example, we will go first we will take that Bernoulli is distribution, that binomial distribution, which is that there are certain process which we tell that it is a Bernoulli process. There is based on some assumptions. So we will discuss those things. First of all, discuss that Bernoulli process, and based on that we will go to that binomial distribution. Even though this binomial distribution is quite simpler, but simpler than other distribution that we have dealt with, but so far as application in different problems is there, it is really an important distribution for different civil engineering problem. Particularly where the outcome is dichotomous, means that there is only two possibilities are there. So at that type of problem can be dealt with this binomial distribution. Then we will go one after another that geometric distribution, and we will discuss about its basic properties, and then we will take this distribution to solve some of the problems in civil engineering. And similarly, after that we will go to that Poisson process, and the Poisson process is also, there are certain assumptions are there, we will discuss that one, and the Poisson distribution we will take to discuss its application to various to handle various problems in civil engineering. So we will start with this Bernoulli process first. These Bernoulli's process are based on some of these assumptions, and these are actually that these properties and these assumptions are discussed in details in the earlier module when we are discussing about that common probability models. So earlier means that in module 3, when we are discussing some of these standard probability distribution, there we have discussed this thing in details. Here we will just quickly go through these properties, and we will directly go to that problems, which is basically the focus of this entire module. So a sequence of n number of repeated trials constitute a Bernoulli process if the following assumptions hold good. The first is there are only two possible outcomes for each trial, which are arbitrarily called success and failure. So as I was telling, that outcome is dichotomous, means there are two possible outcomes are there. So and these outcomes can be arbitrarily called as a success and failure. As also I was mentioned earlier, this success and failure is nothing to do with their linguistic meaning. So any one in any one of this of the outcome can be termed as success, and other one can be failure. Even that tossing a coin, that there are two possible outcomes, one is head and other one is tail. Now if my goal is to get the head, or that I am just going to means do some analysis that when I am going to get the first head or something like that, that means that getting a head might be I can term as success. Similarly, that breaching that embankment of a canal, then I can say that the breaching event is the success, which obviously may not be the case from the social point of view. So this terminology, the success and failure in a Bernoulli process, is completely arbitrarily can be assigned. The second assumption is the probability of success is same for each trial. So that the event that I am designate as success, that probability of that success would be same for each trial. So for example, for tossing a coin, that getting if the coin is fair, then getting the head, if it is I can term as success, then getting the head probability is equals to 0.5, and that 0.5 will not change for whatever trial I go for. Third one is that outcome from different trials are independent. This means that whatever I got earlier trial, the outcome of this earlier trials should not have any influence to the outcome of this present trial. So, the individual trials or successive trials are independent to each other. And the last, there is a fixed number of trials to be conducted. So, this n, so how many trials I am going to conduct, that is known, that is defined prior to the this process starts, and that is designated as that n. So, based on this assumption, now if we want to designate one random variable, that random variable is that if the probability of the success, that is the occurrence of a particular event which we can call as success, that in each trial is given by p, as I was telling. So, this p will not change. Then the probability of getting exactly x successful event among n trials in a Bernoulli sequence. Now, we have to see here that this n trials, this is predefined as was the fourth assumption of this Bernoulli process, and the random number that we are talking here is that the probability of getting exactly x successful events. So, this x, now you can say that x can take any number, any discrete number starting from 0 up to n. So, in an n trials I can get no success, that means x equals to 0, or exactly 1 success, 2 success. Similarly, I can get all n can be the successful trial. So, the random number that we are getting is the number of success out of n trials. So, that random number is distributed through a probability, is a discrete probability function, which is the binomial probability mass function. And this binomial probability mass function is shown in here, that is probability of that x exactly equals to n combination c. So, this is the combination, means that out of n events how many ways you can select x, multiplied by p, which is the probability of success power x, multiplied by 1 minus p power n minus x, the power is n minus x. Now, if we see here, there are some x success and the probability of success is p, and there are, so if there are x success out of n, that means obviously there are n minus x failure, and if there are only 2 possible outcome and the probability of success is p, and obviously probability of failure will be 1 minus p, and as these are independent, that's why we can multiply their probability. So, that is why it is p power x multiplied by 1 minus p power n minus x. This factor, that is n choose x or n combination x, is this, you know that this is n factorial divided by x factorial n minus x, which is this is also known as the binomial coefficient. Now, even though this distribution, as I was telling, may look simpler compared to the other distribution that we have dealt with, but it is having a very wide application to handle different problems in civil engineering. Particularly whenever we see that there are 2 possible outcome of any particular event or any particular phenomenon that we are trying to model, and there I can see, if I can define that there are only 2 possibilities of the outcome, then we will see that whether the other assumptions are satisfied of this Bernoulli's process or not. Then we can model that kind of problems to by this binomial distribution. So, here are 2 examples are given here. Say for example, that the water quality in a river on a downstream side of an industrial plant may or may not meet the population that the pollution control standard on a particular day. Hence, the daily water quality in such a river can be modeled through the binomial distribution. So, you see here that the random variable, that the event that we are talking about is that may or may not meet the pollution control standard. So we are not, so in this type of problem we are not interested what is the level of this pollution, which can be a continuous random variable, but here we are just talking about the two events, means it may meet the pollution control standard or it may not meet the pollution control standard. Now these are daily basis, as it is written that on a particular day. So these are daily basis. So every day I will just see, I will take the data, either it is this has met the standard or this has not met the standard. So there are two possible outcome, and obviously these are independent from each other. The other assumptions, if we satisfy, then this kind of problem can be handled through this binomial distribution. Similarly, the maximum wind speed faced by a structure in a particular year may or may not exceed the design wind speed. Hence, this also can be modeled through the binomial distribution. So each and every structure or any structure when we design, there are several loads that we consider. One is that wind load, which is also one of the most important load while designing the structure. So that we assume some design wind speed for a particular, that depends on various thing, its location, then the type of the structure, and etc. So that design speed, once we decide, and based on that we design the structure. Now the question is that in a particular year whether the design's wind speed may or may not exceed. So each and every year, 1 year I will take, and I will take either of these two information, whether it has exceeded at some event or not. So two outcomes are there, and we can model this one also through the binomial distribution. Similarly, we can think of many other cases, that is, after a rainstorm has occurred in a city, certain critical junction, whether that will be waterlogged or not. So there are two things, so it may waterlog or it may not waterlogged. So like that kind of thing. On a highway stretch, so whether there is some accident or not. So that kind of thing. So here you remember that we are not interested about the quantity, only we are interested that yes or no, that kind of information. So that is the way the random variable is defined in Bernoulli's distribution, the binomial distribution. So if we take one example that in a particular year, so yes, this was where just mentioned, in a particular year a region may or may not be waterlogged due to the heavy flooding. So thus it may be modeled through the binomial distribution, or through a geotechnical problem. If we say that while we go for the soil boring, through that boring there may or may not be some boulders can be encountered for a particular boring. So that boulders may or may not be encountered during a soil boring. So hence this also can be modeled through the binomial distribution. So we will take one of such problem, some numerical problem to see these things. So the problem states, in a series of soil borings, the probability of encountering a boulder is 0.1 in a boring. So here you see that this is the so there are two events, we may encounter a boulder or we may not encounter a boulder. So we may encounter a boulder is, if we arbitrarily term as success, then the probability of the success is known as it was declared, that is that success is 0.1, the probability of that success is 0.1. Now what is the probability that a boulder will be encountered in exactly one boring in the next 5 borings? So what are the information given? So so the fourth assumption of this distribution is that of this process, that Bernoulli process, is that total number of trials should be known beforehand. So here it is written that the next 5 borings. So there are total 5 borings are there, and we are looking for the probability that out of this 5, exactly one boring should encounter the that boulder. So what is the probability of that particular event? So we know the probability of success, we know the n equals to 5 here. So what is the probability to get that exactly one boring should encounter a boulder? Next question is, what is the probability that a boulder will be encountered in at most one boring in the next 5 borings? So now the language is slightly changed. One is that exactly one boring we are interested in the previous question, and now here the at most one boring. So at most one boring means it may be 0 or it may be 1. So we have to just sum up these two probabilities. One is for the 0 encounter, means the 0 means the case number of cases to encounter a boulder is 0, and number of cases encountered a boulder is 1. So if we add these two, then we will get the thing at most one boring in the next 5 borings. So if we solve this one, that the probability of encountering a boulder is 0.1 in any particular boring. So the probability of not encountering a boulder in that particular boring, because you know this is a the two possibilities are there. So the other probability or the probability of failure is the 1 minus 0.1, which is 0.9. Now the probability of encountering a boulder in exactly one of the 5 borings is given by P probability of x equals to 1 is equals to 5c1. There is a ncx that we use there. So 5c1, 0.1 power 1 and 0.9 power 5 minus 1, which if we calculate we will get that 0.328. So exactly one boring will encounter one boulder is equals to 0.328. And the second was that probability of getting at the most one out of these 5 borings is that. So we have to add two such events, the x equals to 0 and probability x equals to 1. And x equals to 1 we have just seen it is 0.328, and probability of facing 0 is 0.59. So 5c0. So nc, now x is here 0, 0.1 power 0 and 0.9 power 5. So if we get this one, this is 0.918, the probability of encountering a boulder at most one of these 5 borings. So another example on this binomial distribution is that a dam was built to a certain height above the mean water level in the river and has a probability of 0.1 of being overtopped. Now here you see that whether the water level of the dam will be such that the water will overtop, and for it has a probability. So that we are now terming as a success, is that whether it is overtopped or not, is that has a probability of 0.1. Then what is the probability that dam will be overtop within the return period? And second is that if the dam is overtopped, then the probability of damage is 80%. What is the probability that dam will be damaged within 3 years? Now to solve this problem, as we have seen that the return period of the event of overtopping is t, which is the inverse of the probability of that event, that is overtopping, that is 1 by 0.1, that is 10 years. So now the question is the probability of overtopping in 10 years. So if so, the 1 minus, if you see this one, that 1 minus 0.1, which is 0.9, this is the probability of not overtopping. Now this probability power 10 is gives that it will not be overtopped in 10 successive years. Now if we want to know that what is the probability of overtopping, then this probability should be subtracted from 1. So by calculating we get that the probability comes to be 0.6513, which is the probability of overtopping in 10 years, that means the return period. So this is first part, and the second part, which is the probability of damage in 3 years. Now we will do this problem in a again that we first will find what is the probability of no damage in 3 years. Now if we see that how many years that it can overtop first, that is in 3 years, it may so happen that none of these 3 years is overtop, so the case is 0. It may so happen that only 1 year is overtopped, or 2 years out of these 3 years is overtopped, or it may be all 3 years. In all 3 years it can be overtopped. Now it is given that if it is overtopped, then the probability of damage is 0.8. So the probability of no damage in 3 years, if we want to calculate, then we have to calculate that for all these 4 cases. Now, if we take that the first one, that is when it is overtopped for 0 cases. Now, if it is not at all overtopped in 3 years, that means the probability of no damage should be equals to 1, because it is not overtopped, so there is no question of overtopped. So that's why that probability is 1. Now, if you just want to expand this one, then you will see this particular case, that is, you know, that C, that is NC, how many times the success is. Now, here n is equals 3 years, and we are saying that it is for 0 years it is overtopped, and then the probability of success is power 0, and this 1 minus p power power 3, that is 3 minus 0 basically. Now, you know, this p is equals to your 0.1, and so this is 0.9 power 3, and this is obviously 1, and this should be multiplied with that chance of damage, and you know that if it is not overtopped, the probability is equals to 1. So, which is basically your 0.1 this 0.1 power 0 multiplied by 0.9 power 3, which is so 1.9 power 3. So, this is the first entry that you can see here in this expression, and the second one is that this 3 is coming from that 3C1, then probability of success, which is 0.1 power 1, and 1 minus 0.1, that is 0.9 power 2, and this is the case when only 1 year out of these 3 years the overtop has happened. So, and that probability of no damage is again 1 minus 0.8, which is 0.2. So, that is multiplied here. Now, if it is the 2 years out of this 3, whether it is overtopped or not, and for that it is no damage, will be the probability of no damage will be 0.2 square, and which is again that this 3 is again that 3C2, 0.1 power 2, and 0.9 power 3 minus 2, that is 1. And similarly, the last one is the case for when all 3 years it is overtopped. Now, if we calculate this one, we will get 0.7738, which is the probability of no damage in 3 years. Now, our question is to get that what is the probability of damage in 3 years, which is subtracted from 1, and it is equals to 0.2262. Okay, next we will go to this geometric distribution. We will first know that what is the difference between this the binomial distribution and this geometric distribution, because both the distribution basically is originates from the same Bernoulli sequence. Now, here in this geometric distribution, it says that if the probability of occurrence of an event in any particular trial P, then the probability that the first occurrence of the event is on the tth trial in a Bernoulli sequence is given by the probability of t equals to t p into 1 minus p power t minus 1. So, what we are looking for, or what is the random variable that we are considering in this geometric distribution, is that how many trials you need to get the first success. So, success again is defined arbitrarily, that is how many trials that we should go. So, here you can see that this probability of success and this out. So, this is power 1, and 1 minus p, this is the probability of failure in t minus 1 event. So, there are total t events are there, out of which one is success, the last one, and this 1 minus p before that t minus 1 cases, this is a failure case. So, that we are interested to know the distribution of this t, that how many trials you need to first get the first successful event. So, this is the this random variable is modeled through this geometric distribution. Now, this mean recurrence time or this return period, that is in a Bernoulli sequence, the average time between two successive occurrence of an event is called the mean recurrence time or return period. The return periods or return period t, this should be period, the return period t is expressed by geometric distribution and is given by that t bar, that is expectation of this t, is equals to t equals to 1 to infinity, t t multiplied by its probability. This you know that how we get this expectation we have discussed in earlier modules. That is, if we get this one, then we will get this infinite series as this. The p is taken common, and this 1 plus 2 into 1 minus p plus 3 into 1 minus p square, and this way. And this is the expression of this infinite series is that p by 1 minus p whole square. So this is 1 by p. So the mean recurrence time of that event, that how frequent that particular event means, here we are talking about that the arbitrarily selected successfully event, how frequently that is occurring is nothing but is that 1 by p, its probability. So this is how that this recurrence time and the that the return period and the probability is related to. We will take one problem on this geometric distribution, that a multi-storied building has been designed against a 30-year earthquake. What is the probability that the design earthquake intensity will be exceeded for the first time on the third year after the structure is built? So here that 30 years earthquake means this is the event that we are talking about, that the event of the earthquake has a return period of 30 years. So the probability of success, again, that having the earthquake is the term as a success. So that the probability of the success we should get from its return period, like the way that we have discussed just now. And the question is, what is the probability that the design earthquake intensity will be exceeded for the first time on the third year after the structure is built? So this is that the first event will occur at the third year itself. So that we can model through this geometric distribution. So the first success after some particular time step, and here it is a third year. And the second question is, what is the probability that the first such earthquake intensity will occur within 3 years after the structure is built? So this is that on the third year, and this is within 3 years itself that design thing that the design earthquake will occur, and which is we have designed for the 30 years earthquake. So to solve this one, first of all we have to get what is the probability of getting such event, and as it is shown in this in the problem, that the probability of occurrence of a 30-year earthquake, so the return period is 30 years here. So that probability of occurrence of such event should be 1 by 30, so which is 0.033. So obviously it is up to 3 decimal is considered. So the probability that the design earthquake intensity will be exceeded for the first time on the third year after the structure is built is given by that t equals to, the probability that t equals to 3 is the p multiplied by 1 minus p n minus 1. So this n minus 1 here is that 3 minus 1, so it is 2. If we get this one, we get the probability equals to 0.0308. So this is the probability that the earthquake will occur at the third year. So you can see that this is quite expected, that when we design the structure for a 30 years return period, so that earthquake will occur at the third year itself. So 1/10 of the total design period. So this obviously the probability will be very less, and we got that probability as 0.0308. The second was that the probability that the first such earthquake intensity will occur within 3 years after the structure is built. Now here the within the 3 years after the structure is built means it can happen any time between that. It may occur in the first year, it may occur in the second year and third year. And we have seen that in the Bernoulli process the successive events are independent. So what we have to do is that we have to get this probability for what is the probability for the event to be occur in the first year, what is the probability that event may occur in the second year, and what is the probability that event may occur in the third year. So these three probabilities we should add up. So this is exactly what is done. So probability t is less than equals to 3 is that t equals to 1 to 3, and this distribution. So 0.033 1 minus 0.033 power t minus 1. So we can put this one as is t equals to 1 first. So we will get this expression t equals to 2 and t equals to 3. So occurring the probability of the occurrence of the event in the first year itself is 0.0333 and then it is 0.0319 and 0.0308 for the third year. So if we add up these probabilities, we get that 0.0960. So the probability that the first such earthquake intensity will occur within the 3 years, we are using the word within the 3 years after the structure is built is 0.0960, which is slightly, obviously this will be slightly more than that what we got in the last one, which is exactly at the third year. It is 0.0308 because we are including the other years also, that is first one and second one. But obviously if we see that there are the return period is 30 years, so that 30 years earthquake intensity is considered in the design. So both these probabilities will be very less, and that's what we got. That second case, it is 0.0960. Okay, next we will discuss about other one, that is the Poisson process. So this is also based on some of this assumption, like similar to that Bernoulli's process. So here the number of occurrences of a particular event within a given time or space interval can be said to be a Poisson process when the following assumptions hold true. Now we can say here is that now the specified duration of the time, or obviously over the space or length of the highway and so, or time means in the temporal directions and number of events over a particular time, over a month, over a year, like that. So now that the duration, the temporal gap or the space limit over which that is defined, and what we are interested to know is that how many such events can occur in this over this duration or over this spatial limits. And the assumptions are a particular event can occur at random at any point in time or space. So, so it has no dependence of this what has been occurred earlier. So if I just consider in the temporal direction, so over, suppose that we are considering a particular time from 0 to t, so it can, that particular event can occur any time within this time frame, and the number of occurrences of an event in a given time or space interval is independent of that in any other non-overlapping time or in intervals. So that is what means, what has occurred earlier, it should be independent of what is going to occur in the next time step. So if we consider to suppose that from the total time span that we are talking about, this 0 to t, and in between that if I just segregate this total time into two parts, and these two parts are non-overlapping to each other, then the number of occurrence for the within the first interval and the second interval should be independent to each other. So basically there is no memory, the process doesn't have any memory what has occurred in the last time step or that last duration of the time. The probability of occurrence of an event in a small interval delta t is given by the lambda delta t. So now if we just consider a small time interval delta t over the time that we are considering, and obviously this can be in the spatial direction also, we can say, we can denote that one as a delta s. So over the small interval of time or the space, that is given by the probability that it will occur in that time interval is the lambda delta t, where this lambda is the mean rate of occurrence of that event. So this lambda is basically, now how we will get is the average that number of occurrence of that time, number of occurrence of that event per unit time. Basically that is what is shown by this parameter lambda. So this lambda is known before we can define a Poisson process. the probability of more than one occurrence of an event in the small interval of delta t is negligible. So, in that small time, so this is basically the infinite simultaneous small. So, in this time in interval, there is the possibility of occurrence of more than one event is negligible, and that is based on what we are just giving, that this is the mean rate of occurrence of that event, which is denoted by lambda. So, as per the assumptions of the Poisson process, the number of occurrences of an event x t in the time t is given by the Poisson process. So, here the random number that we are talking about is that number of occurrences of an event x t. So, over the total time from 0 to that particular time interval t. So, over this interval, what is the total number of occurrence that we are interested here, where this you can see that this t is a continuous variable. So, t can have a continuous length. So, at any point of time it can happen. So, over this continuous time frame, over this continuous time, or it can be space also, over this continuous spatial extent, how many times that particular event can occur. So, when we are looking for this binomial distribution, there are some discrete trials over which how many times that event can occur, and here in the Poisson process, over a continuous time frame or continuous spatial extent, how many times that event can occur. So, this is the random variable whose distribution is given through this one, the probability of this is the variable on which we are expressing this distribution is x, and the parameters is the lambda t. Here you can see that if the lambda is the mean rate of occurrence, then this lambda t is the total number of expected that it can occur within that time interval of t. So, that x t is exactly equals to x is that lambda t power x divided by x factorial e power minus lambda t, where these parameters is lambda is greater than 0, t is greater than 0, and x can take any value from 0, 1, 2 and up to infinity. So, here the support of this x, you can see that it can start from 0 and go up to infinity, all are discrete, the number of occurrences. But in the earlier that binomial distribution, it can take from the 0 to that total number of trials considered, that is up to n. So, here that what it told that this lambda is the mean rate of occurrence, that is the average number of occurrence per unit time. Now, many real life problems in civil engineering can be modeled through this Poisson process. First is that number of occurrences of the flood events, earthquake, hurricanes within a given period. Now, when so in this Poisson distribution, when we are talking about, we are just talking about some discrete variable which is the number of occurrences, but the total time frame that we define should be a continuous one. So, over a given period. So, basically this number of occurrences can happen from 0 to infinity, because this the time frame or the spatial extent we are considering as a continuous medium. The number of occurrences of the boulders within the soil mass. So, for a particular soil boring, so how many boulders can be encountered? So, that is, so in a soil boring means it is from the surface to certain depth. So, in this spatial direction, at any point at any depth that boulder can occur and any numbers of boulder can happen. So, this number of occurrences of boulders within the soil mass or in the within a particular depth of soil boring, that also can be modeled through this Poisson distribution. The number of vehicles taking left turn at an intersection can also be modeled through this Poisson distribution over a particular, obviously over a particular time. So, suppose that in 1 hour these many vehicles will take the left turn at a particular intersection. So, that is can also be modeled through the Poisson distribution. Now, if we take one example of this Poisson distribution, the historical records of rainstorm in a town indicate that in the month of May, the average number of rainstorm is 3 for the last 30 years. So we are considering a particular month of the year, and in that month there is the average number of rainstorm for that town is 3, which is observed for this last 30 years. So this we can say that is the what is the average occurrence of the event. Assuming that the occurrence of the rainstorm is a Poisson process, what is the probability that there would be no rainstorm in the month of May in the next year? So that is the total duration of this time. Any time the rainstorm can occur, and we have seen that over that period it is there is 3 rainstorm is the value that we have seen from the historical record. And the question is that what is the probability that there will be no rainstorm in the next year? Other two questions are what is the probability that there would be exactly 3 rainstorm in the month of May in the next year? What is the probability that there will be 2 or more rainstorms in the month of May in the next year? So basically the first question is we have to say that exactly 0 rainstorm, second one it is exactly 3 rainstorm, and third one is the so that summation of the probability of having 2 or 3 or 4 or 5 or any numbers can go to infinity. And now, so to solve this, the third one, what we can show is that what you can do is that the total probability is 1, and from that 1 we can deduct that what is the probability of the occurrence of the rainstorm, no rainstorm, that is 0 event, 1. We can, if we just sum up these two probabilities, in case of 0 rainstorm and 1 rainstorm, sum up, and if we deduct from the 1, then we will get what is the probability that it will occur 2 or more rainstorms. So without solving, you can say that the probability of this having this 0 rainfall and this exactly 3 rainfall will be much lesser compared to this last one, where we are basically considering all the possibilities except that 0 and 1 case. So here you can see that the average number of the rainstorm in the month of May is 3, that is the mean rate of occurrence, the lambda equals to 3. And now this lambda t, when we are considering here, this is a 1 month, and and there is average occurrence is 3, so this lambda t is equals to 3. And the required number of occurrences here, or the probability that we are looking for the number here, is x equals to 0 for the first case. The probability that there will be no rainstorm in the month of May in a particular year is given by probability x t equals to 0 is equals to lambda t power x divided by x factorial e power lambda x, and now e power lambda t, where this lambda t we know is 3 and this x equals to 0 and lambda t is 3 as is shown. So the probability that there will be no rainstorm, that is number of rainstorm is 0, is equals to 0.0497. Second, the required number of occurrences x is equals to 3 here, 3 here. So number of occurrences of rainstorm is exactly equal to 3. So we have to just put that in place of 0. We will just put 3 now in this expression, and we can see that this number of occurrences here is a 0.224, which is obviously because this is the expected number of occurrences. So these have the higher probability than compared to the earlier case where you have considered the 0 occurrences. Now the third one is that the required number of occurrences is the 2 or more, so that the probability for the occurrences of the rainstorm occurrences x equals to 2 or more, means that includes that x equals to 2, 3, 4, 5 like this up to infinity. So the probability that there will be a 2 or more rainstorm in the month of May in a particular year can be given by basically from x equals to 2 to infinity. Just put this 3, that is the lambda t power x by x factorial e power minus lambda t. So this what I was telling, that this we can calculate just by 1 minus x equals to 0 to 1 of this one. So this total probability, so this from 0 to infinity, this is total is obviously equals to 1 from the basic principle of this probability mass function. The total probability should be equals to 1. So this 1 minus, now we can put this 0, that is we have already got this one, that for x equals to 0 the probability is 0.0497, and similarly for x equals to 1 it will come 0.0248. so that the probability that there will be 2 or more rainstorm in the month of May is 0.9255. So you can see that this is basically taking care of almost a full support of these random variables, which is much higher than compared to the other two cases. So here it is 0.9255. Now another problem on this Poisson distribution is that along a highway the mean number of petrol pumps is 4 per 100 kilometers. So this is now in the spatial direction. Earlier it was in the temporal direction. Now this example is on the spatial direction. So over the length of 100 kilometer, on an average there are 4 petrol pumps are there. Assuming that the location of the petrol pumps along the highway is a Poisson process, means assuming that it is Poisson process means all the assumptions that we have shown earlier should be followed. So, so if we can assume if those assumptions are satisfied, then the question is what is the probability that there would be exactly one petrol pump within the next 25 kilometers, and second, what is the probability that there would be at most 3 petrol pumps within the next 100 kilometers. So the first one, the required number of occurrence here is that x equals to 1 in 25 kilometers, and the average number of petrol pumps is a 4 per 100 kilometer. So in 100 kilometer there are 4, so the mean rate of occurrences of one petrol pump is the 4 by 100. So if this one is, so 1 by 25 is the value of this lambda. Now that lambda t, so here means even though the notation we are using exactly similar to this distribution one, so here the t means that in the spatial direction. So we are interested now in this 25 kilometer. So 25 kilometers, so this t is here 25. So and this lambda equals to the 4 petrol pump per 100 kilometers. So it is 4 by 100. So which is the lambda t is giving the value equals to 1. So the probability that there would be exactly one petrol pump within the next 25 kilometer, that means the x t is equals to 1 with the lambda t value is again equals to 1. So lambda t power x divided by x factorial e power minus lambda t, that means lambda t is 1 power exactly 1 petrol pump, 1 power 1 factorial e power minus 1. So the probability that we get is 0.368, that is within the next 25 kilometer the probability of getting one petrol pump is 0.368. And second is that the required number of occurrences is at most 3 in 100 kilometers. So what is the probability that there will be at the most 3 petrol pumps in the next 100 kilometers. So the average number here again is this 4 by that 100. So the lambda is obviously 4 by 100. Now if we calculate the lambda t in this case, now the t here is your 100 kilometer that we are considering. Lambda is same 4 by 100. So here the lambda t is equals to your 4. Now if we do this one, that the probability that there would be at most 3 petrol pumps in next 100 kilometer is given by that xt is less than equals to 3. So it can happen that there is no petrol pump, there is only one petrol pump, 2 petrol pump or 3 petrol pump. So we have to sum up these probabilities stating that x equals to 0 to 3, and this probability with the lambda t value here, as we have seen in the last slide, that lambda t equals to 4. So it is 4, first case is x equals to 0, so 4 power 0 by 0 factorial e power minus 4. Similarly 4 power 1, then 4 power 2, 4 power 3, these probabilities if we just get, the first one is 0.0183, 0.0732, 0.1464 and 0.1952. So if we add up these things, then we get that 0.4331. So the probability that there will be at most 3 petrol pumps in next 100 kilometer is 0.4331. Now, when we are so this type of problem that we have discussed so far, both in this Bernoulli's distribution and for the for this Poisson distribution, geometric distribution. So there are those parameters, those are the probability of the success is generally obtained from the historical record. Now this historical record, when we are talking about, basically the problems that we are discussing may look that okay, if this information is supplied, then I can get these probabilities. But when we are taking that real life example, then maybe those probabilities we have to obtain from the whatever the data is available to us. For example, the one example we have shown that out of this last 30 years, it has been seen that there are 3 rainstorms in the month of May. So that last 30 years records we can just see, and we can see that maybe in the first year there are 6 rainstorms, second year there is 0, third year there is 4, like that. These things we have to see from the historical record, we have to get those parameters. In this example, that this number of occurrences of this petrol pump 4 in 100 kilometers. So this also we have to see that entire stretch of the entire length of this highway, and from there we have to find out what is the data that is there, and then we can answer this type of probabilitical answer, that what is that at the most 3 petrol pumps in the next 100 kilometer and so on. So that data that we are using for this type of problem can be taken from this whatever the historical record is available to us in case of the temporal direction, or whatever is available on ground in case of the spatial direction. The central limit theorem can be stated as if xi for there are I equals to 1 to n, so that there are the n independent and identically distributed random variables. So this independent and identical distribution, this we have used earlier in other classes also. This means that this x1, x2, x3 up to xn, these are the random variables which are independent to each other and their distributions are identical, and they are from a population with the parameters of this mu and sigma square. So they are all having these parameters. The mean is the mu and the variance is this sigma square. Then the random variable, which is a xn bar, that is the average of all these n random variables, which is we can express as the summation of this all xi's divided by n, which is the arithmetic average. So this is a new random variable, which we can say that it also tends to a normal distribution with the parameters, means mean equals to mu and variance equals to sigma square by n as n approaches to infinity. Now you see here we have not defined any particular distribution of this xi's. So it can have any distribution, but only thing is that whatever the distribution it is having, these are identical distributions. That's what we have defined. But what is their parent distribution? What is the distribution of their particular distribution? This xi's we don't know. So even though we don't know that distribution, then their mean can be a normal distribution with these parameters. Now if we are interested, if we know that the particular random variable that we are considering, which can be considered to be the mean of the several others random variable, even though we don't know what is the distribution of those random variables, we can model this mean as a normal distribution having these parameters mu and sigma square by n. And other things are that if the xi, so the x1, x2 up to xn are normally distributed, if we say that this is normally distributed, then the sampling distribution of its mean follow again a normal distribution for any value of n. So if the parent distributions are normal distribution, then for any values of this n, we can say that their mean will follow the normal distribution with the parameters that we have discussed now. Now it has also been shown that if these xi's are not normally distributed, which means this is the most interesting case, even though these xi's are not normally distributed, then the sampling distribution of its mean tends to approximately normal distribution when the sample size n is greater than 30. So we can safely assume that this mean of this x1, x2 up to xn, if that n is greater than 30, then that mean will be approximately normal distribution with the parameters that we have discussed in the last slide, with the mu and sigma square by n. Now, let us consider that a data set of the densities of the concrete from a particular mix. The data set can be assumed to form a normal population, and the mean and standard deviations are assumed to be 2450 kg per meter cube, and the standard deviation is 25 kg per meter cube. Now, if this is the thing, because now you see that I have given this is as the mean and this is as a standard deviation. Now, because these things we can cast several such concrete from that particular mixed design, and we can have their records, and those records, if we get their mean and standard deviation, we will get this value. So, background to these two data, that is 2450 kg per meter cube and 25 kg per meter cube, is that experiment. So far as the central limit theorem, as per the central limit theorem, the distribution of this xn bar, that mean of their densities, that is the xi by n, will be a normal distribution with parameter mu and sigma square by n is the variance. So from the standard normal table, that is probability that z is less than equals to 0.2575. So this 2575, you know that we have referred to this standard normal table several times, and this is respective to this 99% probability and 99.5. So this is the 99% confidence interval. So the right hand side 0.05 and left hand side 0.05 is left. So this one, if we see, then this x bar minus mu x divided by this standard deviation, that is 25 by the square root of their n, standard deviation by n. This is basically the sigma square. When we are talking about this is 25 square. So the standard deviation will be that square root of 25 square by n. So 25 by square root n. So if we take this one, then we can do this one approximately. It will become as this xi minus mu x to this one, and finally we will get that 0.99 putting this one. So for the small sample size of 25, the 99% confidence interval is estimated, mean density lies within this 12.875 kg per meter cube, say 13 kg per meter cube of the true value. This confidence interval will of course increase with the increase in the standard deviation or decrease in the sample size, as you can see it from here. So this is the true value. So deviation from the true value for the 25 sample size of 2555, if we put that n equals to 25, then it will become as 12.875. Quickly we will see one example. If a concrete cube has an average strength of 25 kN per meter square with a standard deviation of 4 kN per meter square, what is the probability that a sample mean strength of the sample mean strength of a sample of 10 such concrete cubes will be between 23 kN per meter square and 29 kN per meter square. So this we can get from their respective means, and we can reduce variate we can get. Their standard deviation also is known. So this type of problem we have shown earlier, how to refer to the standard normal table and all. So you can get the probability 0.9421. So the probability that a sample mean strength of the sample of 10 such concrete cubes will be between 23 kN per meter cube and 29 kN per meter cube is your this 0.9421, which is the difference between these two. So in this module we have seen that there are several examples has been taken, and this one so the few continuous distribution, few discrete distribution we have taken, and from next module onwards we will see some of these statistics based problem, how to define that different distribution, how to satisfy which distribution is following, and other statistical test we will follow in the next module. Thank you.